For my part in our Biochemistry 2 project, I did the enzyme lactate dehydrogenase, LDH. LDH is present in our muscles and heart. It catalyzes an important reaction that helps provide us with energy through oxidation. So this is the enzyme that I've been studying, lactate dehydrogenase, and this is the 3D space that it occupies. As you can see, it has a tetrameric structure. This means that it has 4 subunits which are depicted in different shades of blue and purple cartoon here. This also means that it has multiple active sites which can catalyze reactions. The active sites each have malonate, MLI in magenta spheres, and NADH in blue spheres. In this video, I will be focusing in on one active site to tell you about lactate dehydrogenase's role in the anaerobic glycolytic pathway. This is a closer look at the actual active site. This is the one active site we will be focusing on. To reiterate, the blue spheres represent NAD, and the magenta spheres represent MLI. If we look a bit closely, we can see the actual pocket that these ligands fit into. To get an even closer look at the active site, we can take away the spheres to reveal this. So this again is the active site, but now NADH and MLI are depicted as sticks. The blue molecule is NADH, and this red region represents the phosphates. In magenta is MLI, which is a biosimilar to pyruvate. If we zoom into the right side of the active site, we can see the main area where the reaction of turning pyruvate into lactate would usually take place. We have the ring of NADH, the malonate ion, and the histidine of LDH. Usually where MLI is located would be where pyruvate should sit in order to move forward with the reaction. However, MLI serves as an inhibitor of LDH, therefore preventing the conversion of pyruvate into lactate. If pyruvate was present instead, the reaction would proceed as follows. First, NADH would have to be oxidized into NAD+. So the nitrogen on the ring would push electrons onto the carbon 4 here to regain aromaticity. So the hydrogens from this position on the aromatic ring of NADH would end up leaving and attaching to pyruvate in the C2 position, resulting in a deprotonated lactate molecule. To protonate the lactate, a hydrogen would be obtained from the histidine here. So in conclusion, we would end up with products of NAD+ and lactate using pyruvate. This reaction is also reversible. Lactate can be converted back into pyruvate and NAD+ back into NADH. This occurs when histidine takes the hydrogen off of lactate, giving electrons to the oxygen on the lactate molecule. So we end up with a deprotonated lactate again. To get pyruvate, we'd have to oxidize lactate by forming a double bond at C2, forcing hydrogen to leave and go to NAD+, giving us NADH and pyruvate from lactate. Here are my references and acknowledgements. Thank you so much for watching.